Raw text is inconvenient for machine processing. We prefer to pass it into an internal representation more amenable to computation. What that looks like depends on the specific problem, but at a minimum you may wish to replace strings of digits with machine numbers, and textual names with unique identifiers. Fortunately, on the build-up to a complete parser, we can isolate some inevitables. Consider this attempt to directly parse text, where low-level character processing is intertwined with structural analysis. In contrast with a tokenized parser, it becomes, hopefully, obviously obtuse. One is easy to read and extend, the other is not. This tokenization is performed by a Lexer, so named because a lexeme is a sequence of characters matching a token. The idea is to simplify text by compressing the stream of characters into a stream of tokens. Lexing identifies character groups so the parser, duly absolved of character-level details, can focus on grammar. Traditionally, this separation of concerns was not an optimization attempt, although neither is it an expense, so long as the Lexer fuses with the parser. That can be achieved by marking the Lexer static inline, whereupon all compilers should manage a few more basic reductions. This fusion is practically guaranteed if you write the Lexer as a non-recursive stepper function, and especially if it doesn't touch memory. Sufficiently motivated as we may already be, we are about to remove all doubt by deploying some advanced optimizations to all aspects of Lexing, from classification to branchlessly eliminating comments and quoted lexemes. It is my great pleasure to introduce VPShufB. Only 8 lanes are animated, but this ingenious instruction performs 16 simultaneous lookups of a 16-byte wide table and manages this in a single cycle. The C intrinsics name is shuffle elements of packed int 8. The value of this shouldn't be understated. Were we to proceed the normal way by addressing memory, we'd run slower by several orders of magnitude. And touching memory creates complications and unpredictable time waste. Even better, AVX512 supplies MM512 shuffle EPI8, which uses 512-bit wide registers to perform 4 VPShufBs for the price of 1. There also exist cross-lane permutation instructions, like MM512 permute xvar EPI8, although that takes 3 cycles, so there are earthly constraints to this miracle after all. Still, much faster than division, and even beats float multiplication. There is one final feature of VPShufB. Only the low 4 bits, called a nybble, form valid indices. The next 3 bits are ignored, but the last is special. If set, the resulting lookup is 0. That will be relevant later. The sub-goal of the Lexer we explore now is character classification. I put the question to you. Suppose I've decided to classify characters in this way, where each set gets a unique number. How should we proceed? It's worth thinking about before the SIMD version comes and obfuscates matters. The clearest solution is a switch. Let the compiler lower that how it pleases. I expect a lookup table, since the alternative tree of branches or dynamic jump should be slower, although they would use less memory. We find GCC made a lookup table and Clang emitted a jump table. The lost time is about 50%. GCC wins this round, and regrettably we should force a lookup table, mostly as charity for Clang. In a more useful application, you'd feed the lookup directly into a parser. Instead, we arbitrarily add them together just to get something testable and benchmarkable. Printing some result is necessary so the compiler doesn't get the idea to skip work. So far, so easy. To distinguish ourselves from the rabble, we now unleash the SIMD performance multiplier. Taking the easy path once more, we could do a byte-wise compare, broadcast a constant, CMP, and move mask. That last instruction collects the high bits of each byte into a general register, bringing us back to familiar scalar territory. Obviously this works, but talking about doing a broadcast CMP move mask for 17 reserved characters sounds prohibitively expensive. Losing to a scalar program using SIMD would be an embarrassment, so we must look for better. VPShufB. Using 4-bit nibbles, we can look up a table of 16 bytes. In other words, we can classify nibbles. We desire to classify bytes, however, so that falls short. But if one VPShufB won't do, how about 2? That gives us coverage of 8 bits, although each lookup is independent. The basic idea, as explained in this paper on SIMD parsing, is to perform two lookups and bitwise AND the results together. In this scheme, we interpret the looked up bytes as 8-bit bit sets, so that a match is confirmed only if both nibbles agree. The result is for each character a single bit encoding its class. If that sounded too easy, you're right. The independence of both lookups allow undesired extra characters to sneak in diagonally. Suppose we desire two characters, a, b, and x, y. If the nibbles are all distinct, we now find ourselves reconstructing extra characters along the diagonals. Perhaps by some insane coincidence that is desired, but realistically, per result bit we need either the high or low nibble to be unique. Now you have some intuition. You'll have to forgive me for temporarily conjuring some magical numbers, so we may expediently execute the plan. VPShufB looks up bit sets for high and low overlapping nibbles. Then, after bitwise AND of the result, I proudly assert we have classified 32 bytes in exactly the same way the lookup table did. I shall even prove it when we get around to benchmarking the results. In the meantime, if we run out of ideas, we can always extract character classes back to scalar registers. MoveMask epi8 collects the high bit of each byte, so it's a matter of shifting the desired bit into place. There is no shift left logical elements of packed int 8, so we have to shift at a higher granularity, which fortunately for this purpose makes no difference. We now have multiple 32-bit bitmasks describing the reserved characters of the input string. Fine, but surely you're indignantly exclaiming, there was unaccounted for magic, and also, the sequence is rather obscure. I'll admit, I chuckled at the thought of offhandedly assigning a new intern to the task of adding a reserved character to this Lexer. Admittedly, dealing with this is hardly a task for human minds, but we are not yet ready to see the automatic derivation. You see, this setup was basically free in that I followed in the footsteps of SIMD-JSON. Yet, it feels off. For example, look how we get the reserved set via CMP equal with zeros and a complement operation. It is a fault of AVX2 to lack CMP not equal. AVX512 is a more complete instruction set. But that aside, there's also a lingering unease with the shuffle masks. But it worked, and is nowhere near a bottleneck. For a while, the sequence survived in this unsatisfactory state. In hindsight, one point immediately jumps out. ASCII is a 7-bit code, so the top bit is irrelevant. Actually, it will always be 0, unless Unicode extensions are involved. And coincidentally, VPShufB zeroes the result if the top bit is set, as it always is in UTF-8 for non-ASCII code points and continuations. Since there is no point in the top bit participating, we may as well double-check the 4th bit of the low nibble. That is more useful, since it reduces the potential for overlapping nibbles and thus increases the set of character sets we can encode. Perhaps our character sets worked out already, but it's still an improvement since we don't need to zero the top bit. Not to be slowed down, I saw the way to get the bitmask of reserved characters directly, using saturating addition. Saturation, instead of overflowing, clamps to the minimum and maximum values, and I distinctly remember noticing these long ago and thinking they're probably underrated. For this next trick, let's set 7 out of 8 bits. Now, adding that with saturation will set the top bit via carry if and only if any bit of the input is set. Thanks to saturation, the top bit is not lost to overflow. That nicely saves us a complement instruction and a constant 0 vector. We need this 7-bit one instead. But wait, the 0xf constant's purpose is to zero out the top bit that is meaningful to shuffle, and by complete random chance, our 7-bit vector is up to the task. And just like that, we save a complement instruction, a constant vector, and we can encode more character sets. I love it when things randomly line up like this. Now we are finally ready to conjure up magic numbers. Since learning the top bit is ignorable, we can pre-compute shuffle controls a little differently, overlapping low and high lookups by 1 bit. We begin with 0 initialized vectors. Then, for each character, for each pair of nibble and index, bitwise OR it into the result bit set. Incidentally, this is done in Haskell, which I'll always prefer over C unless obsessing over performance. Sadly, the Haskell compiler is a study in wasted potential. It has always had the theoretical ability to demolish what one can realistically maintain in C, but we can discuss that another time. Make shuff tables requires as input the desired character set, and does not check for overlap. Remake desired character sets does that instead. I also wrote a function to auto-generate viable character sets. Before that, I somehow got very lucky and randomly chose a viable setup, which later proved to be one of very few possible ones, although the 4th-bit overlap strategy makes this more forgiving. Maybe it wasn't so much luck as ASCII is well laid out. For example, the parens have the same top nibble, so there are no diagonals there. Still, recomputing character sets from marks and checking against the input is a vital sanity check. Perhaps you can see how this heavy list processing with higher order functions would be extremely annoying in C. Anyway, the setup is primitive, and the real endgame is to generate the entire Lexer automatically. Something I'd like to make happen, but neither in C nor Haskell. Now that we've grasped all of the subtleties, we become morally obligated to benchmark the performance. There are pitfalls ahead, including managing my patience for this sort of thing. As obvious an improvement as vectorized classification may be, we mustn't jump to conclusions. Even if you've read all the performance manuals, intuition is overrated. You never quite know what weird things ended up on the silicon. Nor can you easily predict the mischief your compiler is capable of, particularly since we must compile with optimizations or the results are meaningless. The compiler gets the green light to heavily mess with the program. This means no inline attributes are vital, and so is printing the final result, lest it be declared unused and quietly discarded. Despite best efforts, it's hard to say how representative this test is. For example, the first benchmark using Clang shows a 10x speedup. Maybe that sounds good, but frankly, it is astonishingly low. Trying GCC, we register a radically different result, so something is up. The assembly reveals Clang has been clever and vectorized part of our scalar classification, so good job, Clang. But the problem with it trying to be clever is that most of the time it is dumb as a brick. Results are inconsistent, unpredictable, and fragile. For example, if I remove the static inline annotation, then performance dies, and generally small innocuous changes may randomly break auto-vectorization, whereupon your performance has silently abdicated. Interestingly, if we do not static inline the scalar switch function, we find Clang now has the worst performance of all my benchmarks, since it emitted a jump table whereas GCC made a lookup table. The difference in this case is significant. But sadly, neither compiler is consistently ahead of the other, and so all programs are consistently suboptimal. The underlying flaw is the lack of a solid equational theory. Optimizing C-likes is a nightmare. The language is both too loose and too explicit about irrelevant details like memory layout and calling conventions, such that proving a transformation is allowed is often difficult. We conclude that VPShufB classification is around 70 times faster than the scalar lookup. Clang's best attempt was still off by a factor of 10. Of course, once armed with an AVX 512 CPU, an easy attempt to double performance is to double vector width. That is usually trivial minus a few minor details, like the absence of 512 setar epi8 for some reason. And 512 CMP-EQ is now a macro over a more general CMP instruction that returns a mask register. Now place your bets. I'm measuring a 1.4x speedup. How upsetting, I want to double. Who shall we blame for this, since I doubt it's bottlenecking on memory? Ah yes, wasting time with a frame pointer is an unfortunate obsession of Clang, but it can be fixed with some flags. Now it appears a bunch of K-mobs are squandering cycles. GCC doesn't solve it either, and worse, neither can I. The K registers allow all vector operations to be masked, and you can do arithmetic on them, if only our compilers realized this. My guess is they got scared and instantly fled to general registers. Thankfully, we needn't linger on the disappointment. The destiny of these bit strings isn't to be summed, but rather collected once more into SIMD registers. After all, Lexing's 64 bytes in parallel pales beside the allure of Lexing 512 at once.